So on the front of this one, 1 and 2 you did pretty well on. Any questions on number 3? I think you guys did well on 3. 4, I know there were some questions on. On 4, the amount that is left as a function of time is equal to the initial amount times 2 to the power of negative t over our half-life. So here we are left with 100 grams. We started with 600 grams. We're looking for the time. Our half-life is 2,500 years. So to solve this, our first step is going to be to divide by the 600. Now I'm going to leave that as just 1/6. Now most of what we've done has either been 10 to the power of or e to the power of. This one is 2 to the power of, which means we need a log based 2. Our calculator does not have a log base 2 button, so to perform that, we do the change of base. First of all, that cancels out over there. That's just negative t over 2,500. We do a change of base calculation here, which means the log base 2 of 1/6 is the log of 1/6 divided by the log of 2. So on my calculator, log 1 divided by 6, close parentheses, divided by log of 2, negative 2.585. Now to solve for t here, I have to get rid of the 2,500 and the negative, so I'm going to multiply by a negative 2,500. So I'll cancel out the 2,500 and the negative. So here I'm going to multiply by a negative 2,500. Gives us 6462.4. So 6,462.4 years. If we just did 6462, that'd be fine as well. Any questions on that one? 5 and 6, time constants. Anybody have any questions on those two? 6. So for an RL circuit, so this is an RC circuit. We've got farads, that's capacitance. For an RC circuit, the time constant, R times C, so we're looking at 3,500 times 0.00084. Actually 0.00084. Should be 5 zeros, right? Yeah. Come on. There. That looks better. So it's 5 zeros and then the 84. So that comes out to be 0.0294 seconds, or 29.4 milliseconds. If you reverse the order and had the 0.000084 first, it should be the same. Okay. Questions on number 7? Okay. So here we've got a circuit. We are starting out with no charge. We are charging the capacitor here. Our voltage on the capacitor is equal to our full voltage times 1 minus e to the negative t over tau. So our full voltage here is 12 volts times 1 minus e. Our time is 14 milliseconds, so negative 0.014, divided by our time constant is going to be 3,200 ohms times 0.000038 farads. So 12 times 1 minus second e to the power of negative 0.014. .305. That is volts. Number 8. So an RL circuit here. We are looking at no initial current, so we're building the current, increasing the current in that. So our current in the inductor is voltage over resistance. Of course, the current through the inductor will be the same as the current through the resistor. Times 1 minus e to negative t over tau. So again,
for this, if you do like voltage divided by resistance first, times what that number then, that won't change at all, right?
it might give you some round off errors, but it shouldn't be a huge difference. Because that'll be 1 over 60, which would be 0.0166666666. Our time is 0.12, so 0.00012 seconds, divided by tau. Remember, is going to be inductance divided by resistance. So millihenries is 0.250 henries divided by resistance of 1200. So 20 divided by 1200 times parentheses 1 minus second e to the x negative 0.00012 divided by parentheses 0.25 divided by 1200 parentheses 0.007297.00730. So that comes out to be 7.30 milliamps. Okay, 9 through 12 gave you guys a lot of trouble. So let's take a look at those. Yeah, and 10 you did, yep. And 9 you did as well, okay. So number 9, what is the gain for an output voltage of 30 millivolts, or sorry, an input voltage of 30 millivolts and an output voltage of 900 millivolts? So that gain is just 10, whoops, it's volts, so it's going to be 20, right? Times the log of, output is 900 volts over 30 millivolts. Those have to be in the same units. So I'll keep this as 900 and make this 0.03, so now they're both in volts. $89.54 it comes out to be. That'll be dB. The power gain in dB for the input power of 400 milliwatts. And output power of 8 watts. So this is going to be 10 times the log. Output power of 8 watts. I'm going to put that on as 8,000 milliwatts, so they're the same units. And 400 milliwatts on bottom here. So 10 times the log of 8,000 divided by 400 gives us 13.01 dB. Any questions on those two? Number 11, the signal level in millivolts for an antenna with a power at 40 dBmV. So we're told that we have 40 dBmV here. That equals 20 times the log of, we are looking for the signal level. So it's voltage over 1 millivolt. So we're going to divide by 20 here. So 2 equals log of V over 1 millivolt. Do the 10 to the power of, to cancel out the log. 10 to the power of 2 is 100. Equals V over 1 millivolt. So multiply by 1 millivolt. 100 times a millivolt is just 100 millivolts. So the voltage is 100 millivolts. Or you could just say that means the voltage has to be in millivolts, since it's over 1 millivolt. Any questions on that one? You look confused on her.
I just couldn't figure this out in the first class.
Okay. Let's look at number 12. So at number 12 here, what is the power in dBmV for an antenna with a signal of 8 millivolts? So let's do 20 times log of 8 millivolts over 1 millivolt. So that's just going to be 20 times the log of 8 is 18.06 dBmV. Problem number 13 kind of puts these all together in one big unit. So in problem number 13, we have our antenna, and we have a signal level of 900 microvolts at the antenna. From the antenna, we lead off to a plus 16 dB amplifier. That goes through 150 meters of cable into an attenuator of some sort, whether it's a reader or whatever it is. That's going to be a 6 dB loss. 20 meters of cable between there. Another 20 meters of cable going into another amplifier. It's a plus 9 dB. And a final 10 meters of cable going to our end game here, the television, the TV. We want to find the signal level here in millivolts. Or in volts, I should say. So we start out, we have to convert this into a power reading. That's going to be 20 times the log of 0.9 over 1. Why did I change that to 0.9? It has to be in millivolts. 900 microvolts is 0.9 millivolts. So 20 times the log of 0.9. Negative 0.915. Now from that, let's look at our losses. We add up our cable here. We have 200 meters of cable, which is 18 dB, minus 18 dB. We almost have the minus 6 dB here as a loss. That's a negative 24. Well, we've got the 16 and the 9, that's a plus 25, right? Because those are gains. So we've got a loss of 24 and a gain of 25. We've got an overall gain here of plus, this is dBMV here. We got an overall gain of plus 1 dB. Okay, see where that plus 1 came from? We had 200 meters of cables and negative 18. We had negative 6 here, so that's negative 24. Then on the plus side, you got 16 and 9 add up to 25. So negative 24 plus a positive 25 is a plus 1 dB. So from our negative 0.915 that we had before, we are going to add 1 dB to that, which is going to give us a positive 0.085. Bless you. Bless you again. dBMV. So this needs to be converted back to a signal level, to volts. So 0.085 dBMV equals 20 times the log of our voltage over 1 millivolt. So this is going to be, add 1 to this. So that's what it's at. It's actually a 0.0848. We're going to divide by the 20 to solve this. So I was dividing by 20 here. And then we're going to do 10 to the power of. So second log, second answer, which is 1.0098 or 1.01. That's in millivolts. So our signal level at the television is actually slightly higher than the signal level at the antenna because of the amplifiers. Does that make sense now?
Yeah, so I'm doing,
Okay.
I got it all in, so that last part, bringing it back is.
Okay. On this one here, you could do the calculator and you actually figure out all those logs that are numbers. Or the easy way out is to do this. If you're adding logs, log of 2 plus log of x is log of 2 times x. Remember, multiplying two numbers within the log, you can actually split it up and make it separate logs. The log of 2 times x is the log of 2 plus the log of x. We looked at this. Let's say if we had the log of 100 plus the log of 10, that's going to equal the log of 100 times 10. Because this is 2, this is 1. Well, that's log of 1,000 would be 3. So it adds up. Over on the other side, we're going to do the same thing. We're going to start here. 3 times a log, when you're multiplying the log by the number, that number can be a power. So 3 times the log of 8 is the same as log of 8 to the power of 3. When you subtract logs, it's like dividing. So log of 8 to the third minus log of 16 is log of 8 to the third divided by 16. So now we can do 10 to the power of on both sides since we got it down to a single log. This 10 and the log cancel out. That 10 and the log cancel out. We have 2 times x equals 8 to the third over 16. So now it's 8 to the power of 3 divided by 16 is 32. So 2x equals 32. 8 divided by 2. X equals 16. What do you think? Not horrible? Yeah.
So I got the same answer, except for I divided by the logs first.
Yeah, that's fine. Oh, you divided out by the logs first?
Yeah.
You got lucky that it worked out.
Did I?
Yeah.
Okay.
Yeah, you got kind of lucky on that one. Not going to lie to you there.
No, that wouldn't happen.
That would not always happen. Yeah. Okay, so next. Last problem. 32 times 4x minus 6 equals 1024. This one's really an exercise in that change of base formula again. We've got to do a log base 32 here. So so on this side, of course, log base 32 and the 32 cancel out. That's just going to be 4x minus 6. Log of 1024, log base 32 of 1024 is a log of 1024 over log of 32. So log of 1024 divided by log of 32 is 2. So that's just a matter of solving that equation. You add 6 to get 8, divide by 4 to get 2. So x equals 2. Any questions?
Can you explain to me how it works that you have a negative signal strength, but you're still getting the signal? I guess I don't really.
It's not a negative signal strength. It's a negative dB reading.
Okay.
Just because it's a negative dB reading just means it's less than a power of 10, less than 10.
Okay.
Because when you take the log, or less than 1, I should say. Less than 1 millivolt will have a negative reading. If I do the log of 1,
So,
that's 0.
On the phone line, is that negative 48?
A negative 48 dB in a phone line.
Yeah.
So that's negative 48. But if you divide that by 20, and then do the inverse log, oops. So let's try that again. Negative 48. So we're solving for what the actual voltage level is. Divide by 20. That's actually almost 3.98 millivolts is what that signal level is.
So it's okay.
So there's
that
a
was my biggest problem with this. Even the ones that I got right, I went through them so slow because it never looked right to me.
yeah, it's a difficult concept because it's a different number scale than what you're used to seeing. What I'm actually doing here quick is taking this test and putting different numbers in it. And I'm going to give you guys this test to work on as a group and take home and work on.
Substitute out the other one.
Yeah.
Taking over, we got a decent grade on it.
best grade in the class is a D minus.
You would guess that was you, Andy?
I don't know what you get.
60?
I got 67%.
Maybe that's Mike didn't do any better.
Doesn't turn his in.
Yeah.
I just, on two of them, on the one in the front, I don't know what happened. I must have not read my calculator right or something. Two of them on the back, I was looking at the wrong part line limit, so I didn't use the 10 or 20.
What do you think?
And then, apparently I didn't know how to use, I didn't know here the law was supposed to be by 10. That's what it is to get rid of a law of 10, right? You just have to multiply each side by 10.
Pretty much, yeah.
Alright.
10 to the power of. Not multiplied by. 10 to the power of.
Yeah, 10 to the power of whatever number it was.
Yep.
So if you have a log and you sign that, so when they use the log, you need the numbers, right?
Yeah. Here we go. Print these off quick for you.
No, but all the percent is like 54%.
Oh.
Is I didn't know how to do that one thing, so it's snowballed into that problem. I didn't know.
Well, that's fine if you look at it.
It was just the last few problems that involved switching algorithms.
I actually thought you had it there until that last.
I was doing good
Last
until the last
few.
few.
Yep.
I only had one wrong until the last 5. So you can get twice as long too.
No, I just
Yeah.
forgot to change it over to print both sides.
Yeah.
When you guys wanna take one for Mike in case you see him before I do tomorrow?
Probably Hunter.
Of course, that means I gotta come up with a new answer key too. Probably end the recording.